All right, welcome back. So today let's continue working on our project. And for anyone that doesn't know yet, we are working on a language called Croof, which is a really simple proof assistant for math expressions. Right now, we are able to solve things like 1 plus 1, 2 times 2, really simple things. I mean, we could even do more complex stuff by using, variable names. But right now, we are just what we are trying to do with our solver is to define some math expressions in some kind of markup format. It's our Croof custom format where we are able to define functions, we are able to define things like axioms or I guess definitions, like formulas, and then we are asking the solver to evaluate a certain expression. And what the solver will do is it's going to apply depth first search and try to use all the formulas until it reaches some kind of endpoint, and then we are looking at all the leaves and choose the best result, and then we also recreate the parent tree basically with all the steps. So that's kind of how our solver works. It's just a DFS and we get the result. And what I was thinking to do last time was to implement the set of natural numbers, because right now we don't really have any types. Even though we have type checking, we are just not really creating like sets per se. It's just checking that these expressions are valid. But I mean, it is type checking, right? So my current problem is we have to define this successor function, and the reason why we have to define it is because we want to know how to convert from a number to something different that we can use in an easier way. Because imagine that we had to implement plus as an operator. Well, it's way too difficult to say, okay, 1 plus 1 is 2, then 1 plus 2. You would have to define all the possible cases, and that would be pretty crazy, right? So what we did to avoid that was to define this successor function that basically takes in a number and returns number plus 1, right? And the idea is that for the plus operator, we have this definition that just moves the successor from one variable to the other. And this one is basically helping us solve almost all additions, because at some point you are going to get successor of 0, which is 1, right? Or you are going to get 0 at some point, and then you know that 0 plus a is equal to a, which is the other formula that we have. So with only these two definitions, we can avoid defining all of the cases of 1 plus 1 and so on. But we have to define this successor stuff, which is kind of annoying because yeah, you have to write it. So the plan for today would be to try and avoid having to define this thing in here. And what I would like to do instead is come up with another function like we did inside of substitute. And the idea with substitute is it takes in an expression and an implication, which is basically one of these formulas, right? Like this one is an implication, even this one, even though it doesn't have a then symbol, it's still an implication. And what it does, it generates all the possible expressions that you can reach from the current expression if you apply that formula. So it's basically a generate neighbors function, right? So you get an expression like 1 plus 1, and then we are going to iterate over all of these definitions, and we are going to generate all the possible neighbors that you can get from 1 plus 1. And what would be cool is if we manage to just, let's say, delete this part, even this part, and if we do that, then our solver will not know how to solve 1 plus 1 because we don't know how to convert numbers into something else, which is kind of important. So The plan would be to have here a function like substitute built-in, which is going to take in the expression, the implication, and I would like to pass in mutable reference to substitutions. Okay, so let me just copy paste a bit of this. Interesting. Maybe I want to move this one in here, just so it's not needed. Anyway, let me just copy paste this part. So we have this substitute built in. Right, so this is gonna be, oh, I know why I wanted it here, because yeah, fair enough, whatever. It's because we use the relation there. Okay, whatever. Here it's mainly that we only support formulas where the conclusion is just a single equality or like a relation. In the future, I would like to have formulas like exists b and then comma, and then I don't know, you can have even a is greater than b or something, right? So you can have multiple expressions on the right hand side, but that's gonna be pretty difficult. I don't know how to do that, but we'll see. So that's the substitute helper, right? And for the substitute built-in, that's interesting. Do we even need the implication? I don't think we need the implication, right? Because substitute built-in is supposed to work on the expression. Yeah, without the implication. So substitute built-in might even look like this then. Okay, so then maybe we don't even need to call it here, but we need to call it somewhere here, right? So we don't even need to iterate over all the implications. We just need to do it once. Then we do all of this. Yeah, makes sense. So we are going to have substitute built-in helper and substitute built-in is going to work the same. Oops, is going to work the same as back expression node. Is going to work the same as the substitute function. Right. So the plan here would be, we will copy paste this stuff. Built-in. Okay. So what I'm gonna do now is for substitution, in substitute built-in of expression, we need to do something like this. Right. But here we don't really have a formula. That's interesting. Because the parent needs some kind of, yeah, that's interesting. Well, I'd say maybe even here we need to just, because you can see that in here we show what we applied. Maybe I just want to print it, just to store it, like store here the implication, but we don't have it. No, I guess that could work. And let's say that substitute built-in also returns the implication. So what I could do here is call it implication and then just return it here. So, and this one is implication node. And then in here it's implication node. Even though we are like copying a lot of stuff, I guess that's fine. So here we are no longer needing, we don't no longer need that. Okay, and here it's implication. Okay, so we are gonna change it like this. I guess I have to clone it. Oops. And probably here as well. Or I don't know, I don't need to clone it. Okay. All right, and then here is gonna be implication node. And here it's also implication node. Okay, this is implication clone or whatever. Oh, can I maybe just like item and then item clone? I need the dot zero basically, but yeah, let's leave it like this. It's whatever. Okay, and here the result is gonna be, oops, implication node, right? So we change it like that. And now inside of the main function or like the main module, we should have here just the implication. Now, yeah, fair enough. So this should still work. We are no longer showing the number, but I don't think the number was useful anyways. Okay. So then it means that this function needs to also return the implication node. That's kind of annoying because it means we have to build it somehow. Right, and it's like for certain built-in formulas maybe it's not gonna make sense, but yeah, whatever, let's still keep it. Maybe it's gonna be useful, who knows. I mean, we can even have an empty one, I would say. Yeah, we can even have an empty one, so it doesn't even matter, right? Okay, so what do we need to do inside of this thing? We need to match the expression. So match expression, and we need to figure out all the cases. So if we have a set, I'm not sure if we have to do anything. If we have a number, this is one of the cases. If we have a number, we want to be able to replace that number with calling to suc, or I guess successor. If we have a variable, I don't think we can do anything right now about it. So I'm just gonna not do anything, right? If we have a function, this one is gonna be pretty interesting. If we have an operator, this is also like, we could hard code the operators, but I don't really want to. I want to make it suffer, right? And for parentheses, I don't think we can do anything as well. I think it's kind of nothing to do. Okay, but I'm not sure about set and node. I'm just gonna leave them. Okay, so if we have a number, this one is pretty straightforward, although we have to, in the future we might have different kind of numbers. So number node dot, I guess it's we might have numbers that are like floats. Right now we have just number, right? So value, I guess I can clone and unwrap. I mean, I guess instead of, I have to do dot value. Yeah, I mean, it's kind of annoying that I have to call unwrap, but since we have option here, I mean, it is what it is. And we also know that if a token is number, then it needs to have a value. Like, it's impossible to not have a value. So yeah. Okay. So let value, we get a value, right? So this should be a string. Can I do something like let value is equal to value dot read? How do you read a Rust parse int from string? I think it was dot parse, yeah. So value dot parse, and I can even specify the type. And again, I would unwrap here because it needs to have a type. Okay, and probably it's like use 64, the number that we are supporting as the natural numbers. Okay, that's pretty nice. So this is our value. And what can we convert this thing into? Well, let substitution expression. So we have to create an expression node, function, because it's going to be a function. Then we have to say function node new, probably, yeah, new, and it's gonna take in token for the name and the arguments. So token for the name, let's do, so it's simply token, wait, it's not important, token value, and here we have to pass token kind identifier. It's an identifier, and the name is going to be suk, the successor. And then for the arguments, we'll see, let's leave it like this. And then we have to say substitute. Oh, we also need the implication node. Okay, let's do here expression node. Ah, really? Huh. Okay, expression node dot number. Then we have a number node new token value, token kind is number, and the value should be value dot to string. So this is going to be our argument. Kind of wrong. Whoa. But this should be the substitution, right? So we just replace a number with this thing. Again, kind of weird that we just have the string here. Maybe we'll have it defined somewhere so that, you know, we don't use magic strings. Use const, but we'll leave it like this for now. And the implication node. This is going to be interesting. Oh, here it's not right. I need to say value -1, right? Because 1 becomes successor of 0. Okay, anyways. Okay, and let implication is gonna be an implication node. Let's do new. And implication node takes as an argument the conditions and the conclusions. So conditions, pretty straightforward, is just an empty vec because we don't have any conditions for this thing to happen. And the conclusion should be this, or I guess number is equal to that. So let's also have let number, and I'm just gonna vi squarely brace. So this is for the number, and the second argument, so it wants statement node. Whoa. Statement node new. Oh, it doesn't have a new? Oh, it's a relation. A relation node. It's, if you remember from the stack language, when we actually rewrote the language in itself, and we had to define all of these, like we had to define things like this for the built-in functions, and man, that was insane. Like in a stack-based language, to define all of these things was so hard. Anyway, but I mean, it was pretty fun, not gonna lie. So this needs the relation kind. Relation kind equality. Right, it wants a token for the equality symbol. So token new token kind equal. And the cool thing about these tokens is that we don't really care about the position or the source ID, right? Don't really care about them. Okay, so that's gonna be that, but we still need the left hand side and the right hand side. So the left hand side is gonna be the number, but I think I have to clone it, and the substitution.clone. Right, so this is gonna be the statement that we have to add in here. This is the implication, this is the substitution, so we just have to push it into substitutions. Okay, so substitutions dot push, was it push? Yeah, expression and implication. Oh, so it wants clone. Yeah. So this is pretty cool. We are able to just generate this successor function, right, pretty easily. And for the other case, which is if we have a function right? What I would say is maybe let's do a match. Match function node dot name dot value. Can I just unwrap it? Can I do successor to do and anything else to do? If I reference it, nope. As ref, I guess I have to clone it. Okay, it's pretty ugly. Maybe I want a function that returns the value and calls all of these things, but we'll see. So if we have anything else, we are not gonna do anything for now. We don't really care. But if we have the successor function, then we need to define some things like this. So one of them is gonna be the arguments, right? So we need to find the argument. Let value. So we know it's gonna be only one argument and it's gonna be a number because we did type checking, right? So we did type checking, so we should know that that's true. So value function node dot arguments. So arguments is a vec. So I can just take the first and unwrap. So this is gonna give me an expression, right? So I can maybe let the value it's just like we do it here. I can just copy paste this thing. What the fuck? Okay, whatever. So let's do something like this. Let expression node number is value. So we take I guess I could just say value here. I'm not sure if I can do like value dot anyway, probably I can do it here already. So I can just say else panic expected number right. So we just expect a number there. Okay, perfect. Oh, even here, that's interesting. We don't even need this number to be defined. We can just use the expression itself just to save some lines. Anyway, so here we get the number, right? We have to parse it. So let's parse the number. Again, we know it's an integer. We know it's unsigned 64, so that should be good. Value dot clone dot unwrap. So again, it should work. Whoa, what the fuck? Value dot value dot value. I mean, yeah, it is what it is. Right? And we should create a substitution. I mean, in this case, the substitution is gonna be pretty simple because we are gonna do a number. So substitution is gonna be expression number node new token, and we're gonna do +1 +1. Nice. And convert it to a string. So that's how we are gonna get the substitution. Then for the implication, we're just gonna copy paste it. And in here, we have the same stuff, no preconditions, only the conclusion. And we have an equality between expression and substitution. Yeah, that's right. So that's how we are gonna generate all of these, like built-in functionalities. Okay, so let's see here. If I do print ln and I say built-in, apply, and then I just substitution and implication. Oh, what? Let's print something just in case. So it gets in here. That's good. That's good news. Do we get into the number node stuff? Number node expression. Not really, what the fuck? Yeah. So I guess what we are missing actually is if we have an operator or parenthesis, we should and even for a function, if it's the other case, we have to do something else. But if it's an operator, we have to try built-in on left hand side and on right hand side. So we still have to do that recursive step. So just like we did with substitute helper, we have to call something similar on left substitutions and on right hand side substitutions. Interesting. So let me just copy paste these two, left hand side and right hand side. We'll go in here and I'm gonna say left substitutions. We are gonna do substitute built in, right? And substitute built in takes in the expression, so the left hand side. Why did I say expression node? I mean, it's expression. No. Interesting why. Oh, what? I guess it's called expression node, whatever. Expression node. Even here, I guess it's expression node, just to keep the same kind of format. Right. Anyway, it doesn't really matter. So we do substitute built-in. We get left substituted, which is expression in implication. So what do we want to have here? So it's left expression and left implication. Left expr and left impl. All right. We clone the node. We set the left expression to be equal to left expression, and then we create a new operator node with left impl. So this should fix it. And for the right, I'm just gonna replace left with right. Straightforward, I guess. GI. Okay, so this should solve the problem with plus, right? Because now it should try to use the built-in stuff, but it's pretty interesting. But it does try to apply 1 is equal to successor 0. Apply 1 is equal to successor 0, but why don't we get anything interesting? Maybe I want to print ln here something like substitution. I don't even need to apply. I just want to see the Let's see, that's like the substitution looked the same for some reason. The fuck? So here an expression clone. Wait, what? Oh shit, here I did expression. I should have done substitute. I don't know why I did expression. Substitution. Okay, and here as well it's substitution. I don't know why it didn't show me. Wait, it probably did. Right, it showed me that it's unused. Still weird. Substitute. Oh, because it's used here. Okay, yeah. Shit. Anyway, so let's see. Whoa, that sucks. So we try that, then it tries this one, it tries that. Panicked at 222. Oops. I know why, because yeah, it's if it gets to 0, then you cannot, it's like the base case, right? So I guess if value is equal to 0, then it's the base case and you cannot really do anything. Wait, how do I break? I guess I just return. Right, that's like a base case. Panic format. The fuck? 247. Expected a number. Okay. I guess. Okay, let's think about it, because this one is interesting. So let's say we have a function and we know that the type of the argument is n, but it doesn't mean it's a number. So it means that I have to do a match. Let's do it like this. Okay, so fill the arms. So if it's a number, we are gonna do something. If it's anything else, we don't care. right? Because if it's anything else, we don't have a definition for that. Or I guess we don't have an edge case or a built-in case, should I say. Okay, so here we have a number node. So it's number node dot value dot value. Okay, fair enough. Oh, whoa, what the fuck? I mean, it was slow as usual, but at least it got the thing done. All right, so now we are no longer basing our, you know, so for instance here it's going to apply 1 is equal to successor 0 without actually doing without actually defining this in the Croof file, so it's built in. All right, that's pretty nice. So 1 plus 1, we start with 1 plus 1, right? This is like the step-by-step solution. We start with 1 plus 1, it turns 1 into successor 0 plus 1, then it uses the shift, I guess let's call it shift, right? It shifts the successor from here to the 1, and then we have 0 plus successor 1, it applies this built-in thingy, and then it applies the 0 plus a formula, and we get a 2, which is pretty nice. So we are actually supporting now the built-in stuff, right? That's kind of cool. So next step, oops, if we look at Croof, maybe I don't even want to define this thing here. Maybe I want to define it also in the AST, kind of, right? So yeah, maybe the type checker has to do it. So if we go to main, we are calling the type checker here with all the defines, and we check each implication, right? So maybe when I'm calling to new, I have to generate all of these defines here. Right, for stuff like being able to define successor n or whatnot. Here I'm also hard coding a type of a number is capital N. So yeah, that's also interesting to see. Yeah, I guess that could work, just defining it here. So what I would do is let mutable defines is equal to this thing, right? And then just that. Right, and at this point I would like to add, so let's cat it. Oops. It's like I would like to add this thing into here. Oh, what the fuck? So defines dot, cannot I just push? It's because it collects it into what? The defines is a hash map. So defines the insert. So we have basically suk to string, right? And the value should be just the types. So type node. So type node new, and this one takes in a vec. So it's gonna be vec, and inside of the vec we can just do, so type node is a vec of tokens. Token, man, it's so annoying. Token, like it doesn't show me the LSP when I'm in the macro stuff. Anyway, so token kind, do I have type? I do, and then n. So this is gonna be the type of this function. Wait, but insert is, that's a hash map, what the fuck? Collect hash map. Yeah, weird. Anyway, so we add successor as a function here. That means that we don't even need to define it here. So this should still work. Right, that's pretty nice. Okay. But then, for instance, this one, we need it, right? And it's also interesting, like here we are just defining variables or like functions, right? But you should also be able to define a set if you want to define a new set. So yeah, I'm not sure. Okay, let me just do here pub const function successor, and I just use this function successor. So here we can just function successor, right? And when we're using successor here, for instance, we can just say function successor. Right, that's pretty nice. So we are defining it here, and then we are able to use it. Maybe also type n. Let's do pub const type n is an str. What the fuck? Type n, type n, type n. Right, and I don't think I use it anywhere else. So yeah, I think that's just defining the natural numbers basically. Okay. So I think the last step probably that I would like to do, let's first of all have something like example.croof. So what I would like to showcase, it's doing one plus one, let's see. Evaluate 1 plus 1, right? But I need to define plus. Actually, I'm just gonna copy paste the stuff that's needed for this one. So I think we only need this. I don't think we need parentheses, so that's that. And if I run it on example Croof, it should be pretty easy, right? To do it. But what if I do 100 plus 1? Well, it stopped because I added a depth limit. So, and it's even worse than 100 plus 1. Okay, so inside of the solver, we have this depth limit, right? Which is kind of annoying. Right, like at this point it reaches 101, which is the right answer. But the problem, if you see what happens, is it always just applies the successor function and it keeps going, right? It doesn't try something different. And I guess even if I would add back this one, even then, like what it can do here, like the shortest path possible, would be to apply this formula. It reaches 1 plus 100, then it applies this successor thingy, or I guess it has to apply successor 1 for this one, then it applies this, and 0 plus a. Right, it should be extremely straightforward to solve this one, but you can see it takes, and it does those steps. It first applies like depth first, but it goes until it cannot go any further, basically. So what I think I want to do is to try and have a really basic BFS approach, just to compare it. Right, so now obviously it got the better solution that I was talking about, but it still feels like it took a lot of time. And yeah, I guess you can play around with this and say, okay, keep it at 50 and it's gonna be faster, but it's kind of, yeah, so it was faster now, but that's only because I played with the depth. And this is kind of annoying because what if, like, you cannot really control the depth. So let's try to have a solve BFS and see if it helps. So how is solve BFS gonna work? Solve BFS. It needs reference to self, it needs the expression. I'm not sure what it's gonna return though. Probably it's just gonna return this stuff straight up. Okay. So it needs visited parent, I guess. I guess it needs these two. It needs a queue for the substitutions for the neighbors, basically. So I want let mutable q is vec new, is a vec new. And maybe inside of the queue, I'm just gonna put the expression first. So it's gonna be a vec with the expression. Okay, so with the expression. Okay. So that's the first step. And then I guess while the queue dot is empty, that's false, we should be able to say something like let expression is equal to q pop, but I want to pop the first element. How do you pop first element? Just vec pop first. Okay. And what if we use a vec deck then? Vec deck q dot push back the expression q pop front. And I guess while let sum, we could, I don't know if this works honestly with while loops. Let me just, okay, this page, okay. So it does kind of work. So we get the expression here. So what we need is to, I guess we want to visit the expression. Probably we want to do something like this. So we want to visit the current expression, right? We popped it and we visit it. Then we generate all the built-in, we parent insert because we visit that path. And then instead of calling recursively to solve DFS, we want to push into the queue the implication. So q dot push back substitution without capital V, but you know, expected, okay. And here as well, we push that. And at the end, we just want to create this result and steps. So this would be, oh, what do I mean? I have to clone it. I don't mind. Just clone this bitch. Whoa, what? The fuck? Interesting. Let substitute. The fuck is this shit? I guess I had to clone it here and then it's fine, right? Or what? Substitute. Okay, fine. So I guess the type of the vec was weird. Anyway, so solve BFS should work similarly, but instead of going in depth and finding the like each solution individually, it first tries to find all solutions at once, basically. And maybe one interesting case that we can make here is if expression dot degree is equal to 0, I think we should be able to break. Right, so if we reach some kind of case where we find a solution, we just stop. And since it's like looking in parallel instead of only one path, we have greater chances, I would say. I don't know, we'll see. So let's switch from solve. Let's try to use solve BFS. So what would happen here? Ah, shit. What did I do wrong? Println expression. Who the fuck knows what I did wrong? Oh, but it gets to expression 101. So what's wrong then? It was result. Result is visited, min by key. Okay, then what I'm gonna do instead of just calling break, I'm just gonna do the return there. And then otherwise it's no solution was found. Because I don't know why. This is stupid. So let's do something like return. Error. Solver error. I know I called it to do. No solution was found. Okay, interesting. I mean, I guess I was using format. Yeah, whatever. For, and then we can just pass here the expression. Yeah, whatever. So here we don't need to check visited because we already have the expression with the minimum degree, basically. Okay, so the result is just expression. And this function is like, yeah. Steps. Let me just move it then. So here it's like steps. Fuck. Hmm. 408. 408. Ah, yeah. It's whatever. Okay, so now we get 101. That's cool. So the other one was test Croof. Let's see if test. I mean, printing, yeah, has to be slow, but this would also find the shortest solution, actually, right? So I think I want to keep the. Maybe I'm gonna do a like. Let's call this one helper, and this one solve DFS, and here's some DFS helper. I'm gonna keep both just because, but I think solve DFS helper. retrace steps. Retrace, or I guess trace steps, I don't know. So like, see, it gets it with the easiest approach, right? Even for 2 times 2 it's much shorter. So BFS actually gives you the shortest path, while DFS, I guess, it gives you the first path it finds. So maybe that's kind of the difference between them. So here you can see that it applied successor 1, then wait, what? Successor 1. Ah yeah, so it's this, it results this, then it applies successor a times b is a times b plus b, so it gets this, then it applied this stuff, then it switched them around apparently, then it did suck 1, then it applied this thing, then it applied this thing, then 1 plus 3. I mean, it looks clean, right? Even this one. So I would be kind of okay with this approach. Let's do a harder one. Let's do 4 times 7. Let's keep on it 4 times 7. Let's see if it can actually solve it. Or is it gonna die trying? I mean, I assume it's gonna be a really long solution, to be honest. So at this point we might be able to think about some heuristics, like if the expression grows too much, then you know it's not the right solution. Maybe. And also what, even though it is slow right now, I'd say you can actually just see the advantage of using Rust compared to C, mainly in the memory usage, because with C, it's not that it's easy to use C, right? It's a really simple language. The problem is once the project grows, it becomes a bit complex. You have to deal with all that memory usage, and it kind of sucks because even though C is really fast, if you make mistakes in like logic mistakes, right? Even Python becomes faster because you are using the memory wrong. So it's not really true that, wow, C, it's so fast. It's fast if you know how to use it. If you don't know how to use it, then even Python is better, right? Like that's why I think some, corporate developers actually use JavaScript. I don't know why why JavaScript came into, yeah, whatever. But yeah, it's kind of slow. So let's give up. Let's do a simpler. Let's do 3 times 3. Come on, this should be extremely easy. 3 times 3. We did 2 times 2, so it's time for a 3 times 3. In the meanwhile, while it's battling it out, let's try to define some other operators. So we have plus, we have multiplication, but I mean, if it's not finishing this, what are the chances of doing that? Okay, so I guess another good one would be this one. Let's say it's 4 numbers, right? So what it's supposed to do is for all a in n, a to the power of 0 is 1. For all a in n. I guess, do we need identity as well? So we need like 0 becomes 1, 1 is just a, and then what about and b in n? What if we do a to the power of successor b? Right, that's interesting. So this would result in a times, shit, I need to use parentheses. Oh, actually I don't think I need parentheses, but maybe I'm gonna do it like this: a times a to the power of b times a. Right, so it looks exactly like multiplication. So that's that. But then the problem is, what if I want to convert a with successor? I don't think that's possible. So let's just leave it like this. God damn, it's still not done. Wow, this is sad. 3 times 2. Oh, it's because we don't have a caret as a symbol. So let's go into the lexer and let's add c equals to caret. Expected equal found column where? Line 25, 17. Line 25. For all. Forgot about the other for all. Wait, what? Did I put a then or whatever? I mean, we still have 3 times 2, which was not great. So let's do 2 to the power of 2. Let's see. Then now we have so many formulas, it might be even slower. So that's also a good point. The more formulas you add, the slower it's going to become, because yeah, it's going to have to try multiple paths. That kind of sucks. Whoa. Let's see 2 times 2. Let's see, really? 2 times 2. I mean, that's sad. So yeah, like adding an heuristic is probably what we need at this point, because otherwise it's gonna be stupid slow. But you know, at least we managed to implement the natural numbers. Yeah, I mean, it's kind of disappointing that it's this slow, but it is what it is. I was just thinking, like, maybe being able to add some other things would be cool. Like, how would I implement, for instance, this operator, and to boolean, right? But I would also have to define a way to, or like find a way to define set. Wait, how do I handle that in the parser? How do we define sets? So a set like we can find random sets. But I don't think we really define like a real set. Like for instance, I would like to be able to do something like this, true and false, but we don't have string parsing at this point, so we might have to add string parsing. Right, but pretend we have these things. We define the less than operator. Then how would we think about this one? Well, first of all, let me just do something. Let's go into the solver and solve BFS. Actually, let's try to use solve DFS, see if that helps. Doesn't. Okay, whatever. I wanted to print the expressions, so it's like println try expression or something. So at least it shows what expressions it tries, right? Even though they're going pretty fast. Whatever, I'm just gonna leave it. Although would be better if I see something like expression goes into substitution by using this invocation. So substitution and invocation. Right. Okay, like clone them, whatever. Do the Rust stuff. Okay. Actually, I'm just gonna print it before. So now it's gonna show us this thing, and then this thing. So maybe I don't know, we'll spot something. So for Croof, again, how can we actually define something like this function? That would be pretty nice. So let's say it's for all a in n. Maybe we have to say exists b in n. Or maybe it's like for all b in n, if a is less than b, then usually you also have for all c in n, a is less than b, and b is less than c, then you also have a is less than c. This is like the transitivity or something, I don't know. So yeah, the expression looks kind of huge. Now I like just by 1 times 1 times 2 to the power of 0. Yeah, they're not the same. Anyway, so maybe something like this, but this is like a recursive definition, so we need the base case. Right, so how do you define the base case? Like maybe one base case is for all a in n, then successor of a, or I guess a is less than successor of a. That's one base case, but yeah, maybe for all a in n, b in n, then we have that a is less than a plus b. That's also something, but not really, because b has to be greater than 0. Right, so I would need maybe a condition here, 0 is less than b, and maybe another maybe another condition that's interesting is for all a in n, 0 is less than successor of a. Right, because if you apply successor on any number, you get something greater than 0. But see here, at this point, we need these conditions. And we also don't know how to define new sets. So maybe I'll add a keyword like set, just so we don't screw around with dev. So it's just set, like a new keyword, doesn't really matter. And then we might be able to do things like this. But again, problem is the preconditions. We need a way to check them. Like being able to apply formula, it means you have to check this thing to be true. Right. I mean, I could say here +1, but yeah. Yeah, I mean, this would be interesting to look into how to do something like this. But man, it's crazy, it's still going. Yeah. Yeah, again, like if it grows too much, it doesn't know how to solve it. So maybe we want to first of all look into some kind of strategy to improve the performance. Like some kind of heuristic, trying to use something like A star for searching, because it should be possible to use, like, it's a search problem after all, so A star makes most sense, honestly. I'm just gonna remove these. So probably trying to use something like A star, right, with an heuristic. But you know, how do you compute the heuristic? Because we don't know the solution. Or I guess we know that the solution's degree is 0, but we don't know the solution. So yeah, that's gonna be interesting. But at least we are able to solve simple things like 2 times 2. Right. Yeah, like it knows how to solve the simplest expressions, and it's also doing it in the shortest path. So that's decent. So yeah, I mean, hopefully this was interesting for you, like being able to hard code those functions into the interpreter basically. So yeah, hopefully it was interesting. So see you.